so last time the two things that we went through that. So basically, if you want to know the shear or normal or bending at a given point, how to calculate that. And it said that if you want to design a beam or any element, so we need to know the shear and bending in the entire element. So we know that where it's going to be maximized and then design that element for that point where everything is going to be at its max.
We have to worry about torsion, right? Torsion as well.
In the strengths of material, we will do that as well. But for now, we'll stick to the shear and the moment. So I gave you just the quick idea of how we do that. So you have to establish the X at the beginning of the beam and keep cutting through the beam and find the moment and shear based on that. Remember that before you're going to do some example for that. Anytime there is a change in the force, we need a new section. And anytime we have a distributed load, we need one section in the middle of, somewhere in the middle of that distributed load. So let's look at a couple of examples.
Which page are you on?
343.
340.
Yeah. So this is the simple one. Okay, first, it's a simple beam. And somehow I'm going to make it a little bit different from there to make it a little simpler. It's a simple beam, 5,000 newtons sitting right in the center of that. And the 4 meter the 2 meter, and A and C. So that's A, point B, right in the middle, and the point C. So I want to find the moment and shear diagram for that. So the first step that I have to go and find the reaction of the support, because there's no way that I cut it in a half and I end up using the reaction of support. If I cut it in a half and there's one half that doesn't have any reaction, so I can use that half. So I don't need to calculate the reaction and so forth. But here, anywhere I cut, I will end up with the reaction of support. So I'm going to have them. So I have to find those reactions. So it's going to be AX, AY, and CY. The reaction I have. So if I write it for entire AC, so I can find the reaction of the support, write the sigma of x0, so AX will be 0. And the sigma of y doesn't help me, so if I write the sigma m is 0, let's say about A. If we write it about it, I have the Cy times 4, let's write it, Cy times 4 minus 5,000 times it's 5,000 times 2 is 0, so Cy would be 2,500. And then if I write the sigma Fy 0, Ay will be 2,500 as well. And you could have said that just by looking at it, because There's no horizontal force, so AX is 0, and it's completely symmetric. So that 5,000 is going to be divided by 2 on both supports. So now I want to find the equation for the shear and the moment. I have to cut any time that I have a change in the force. So if I start from here, there's a change in the force, so I have to have the section there. So basically between these two forces, there's a two concentrated force. I have to cut it somewhere in between there. Again, where we don't know exactly the position, but we know that it's going to be somewhere in the AB. Somewhere in that region. So I would say for AB, so if I cut that, the AB part, so if I cut it somewhere there, and I know this is the A, B is somewhere here, so it's the A. The external force AY applied there, 2500. And then I have normal, shear, and M. In this case, we are not interested in normal because we are looking for the shear and moment. We don't need to calculate it. If we do it, we do it, but instead we don't need to calculate. Now look at here. This first section I'm cutting is somewhere here. That's section 1. And that's going to be the section 1 here. So it's the A to 1. The next thing is that I have to establish the X coordinate, always start from the very left of the beam. So I have to have the X coordinate and to start from here to this section I just cut. So for the X, what's going to be the range for the X? X is going to be between 0, it can be somewhere at 0, up to 2. It can be somewhere in between there. So X, I will write there that my X is between 0 and 2. It can be 0, it can be anywhere between them, or it can be 2. So now I want to write the equation. Sigma of x0, it gives me the n is 0. Again, you are not interested in the n, but anyway, just look at it. Sigma fy is 0. So 2500 minus v, and function of x here, minus v would be 0. Therefore, v would be 2500 Newton. And then I can write sigma m is 0 counterclockwise positive. And then if I write it about the center, what I have is that I'll write it down here. I have 2500 times, if I write it about that, look here, if I write the moment about point x, is it 2500 and the arm of the moment would be
X.
the x. So that is where the arm of the moment, that's where the x is entering your calculation. So 2500 times x, and it's going to be counterclockwise, so it's going to be negative. So it's going to be clockwise. Negative plus m would be 0. So m would be 2500 x. Newton meter. So if you look at here, for that range, for x being between 0 and 2, this is the equation for the v, and this is the equation for the m.
So normally the moment is, so like for the AC, that's the moment of point A, about point A. But then for AB, is that still the moment about point A?
Which one? Which one you're talking here?
Yeah.
Is it about, I took it about point that section.
Okay, it's just that section.
About that section.
Right.
One. Usually it's easier to cut to get the moment about the section, but you can take it about any point. It's going to give you the sections. So now I know what happened as a function of x between a and b. Now I want to see what happened as a function of x between b and c. So next, remember I said between any time in 2 points or where there is a change in the force, I have to cut. So I cut it. Now I move on, I reach the point B, there's a change in the force. So I have again to cut, I have another cut there. So I have to go ahead and make another cut anywhere there. So for BC, so if I make it for the BC, then I have 2500 here. I have 5000 here. So this is the section 2. I have the N, I have the V, I have the M. This distance is 2. And again, x start from the very left of the beam. So x will just start from here to this section. That's going to be x. From the beginning of the beam to where you cut it. That would be the x. Where would be the range of the x this time? 4, 2 to 4. Because we want to cut it between B and C, so it starts at 2 and end at 4. So x would be equal or greater than 2 or equal greater than smaller than 4. Again, we have to write the same thing, so I go ahead and write sigma f x is 0, gives us n is 0. Then we have this sigma fy is 0. So I have 2500 minus 5000 minus v would be 0. So v would be minus 25,000. Right?
Yeah.
So negative 25,000 years. And then the moment, if I go ahead and say, okay, I want to find the moment about the section point 2 counterclockwise positive is 0. I write it from there. So the first one is 2500, and it's going to be processed at 2500. So the arm for the 2500 is
X.
what here is going to be the x. So times x. Then I have 5000. What's the arm for the 5000?
X minus 2.
So x minus 2. So arm for there is going to be this distance here. This distance here. This would be x minus 2. That's going to be multiplied by x minus 2 plus m is equal. Which they have it right, it should comes out as m equal to 10 minus 2500x So for that range, for x being between 2 and 4, that is my shear, and this is my moment. So any question over here? Now we have to plot them.
You have to do what?
Plot them. So I have to go there and start plotting them. So I go there and say, okay, let me have two axes here. So it's going to be there. This one is going to be V. This one is going to be the M and X. And brown So for the V between 0 and 2, the V is 2500 constant. So the V is going to be 2500 constant. When I reach the point B, between the B and C, it becomes negative 2500. Again, it's constant, it's not changing there, so it's going to become. So that's going to be my plot for the V. So start from 0, there, there. Now I want to draw that for the X. So if I go ahead here, if I put the X 0, it would be 0. So it's going to be 0 at here. At 2 meter, if I put the x2, it's going to be 5000. And look at it, it's a linear equation. It's a linear equation, so I don't need to find any point in between, because it linearly goes there. Now here, if I put 2 here,
Negative 5,000.
that's it.
Oh, well, yeah, plus the 10,000 makes it then positive 5,000.
So still it's going to be the same point there. So if this is 5000, so it's going to be starting at 5000. And if I put 4 there, goes back to 0. And it is linear, so I don't need to find anything in between. So for that beam, under that load, this is how the shear change in my beam. This is how the moment change in the beam. So if I want to design it, I know that the shear is always 2500, either positive or negative, so I have to design it for 2500. If I want to design it for the moment, I have to design it for 5000, because that's the maximum it's going to happen. Any question? So that's the simplest one that I'm going to do one more example. And the procedure is the same. It's just it's similar to that. You're just gonna have just much more step, much more cutting. But process would be the same. Okay, so we have the beam like that. There's a distributed load there. I want to find again the moment and the shear diagram in that. So the very first step is again, I have to find the reaction of the support. So I have to go there and say, okay, I have here AX, we know that's going to be 0, AY, and BY. So these are the reaction of the support I would have. Again, I have to write it for the entire beam. Let's call it the last point C. Call it C. So for the AC, for the entire beam, so I can write the sigma of x is 0, gives me the AX is 0. I can write this sigma y 0 doesn't help me. I can write the sigma m about A probably 0. And I can write the moment equation for that. AY, BY. By writing about point A side, I would have the BY times 4. It's going to counterclockwise. Minus the equivalent of that force applying at the center. So it's going to be 4,000 times 2. And the distance is going to be 4 plus 1. 0. Gives you a BY. I'm just going to do this part a little bit quicker so you can get to actual force. So that's the force there. So that is 4,000 times 2. If that and this distance is 1. And if I write the sigma Fy 0, so By comes out as 10,000. And if I write the sigma Fy 0, Ay should come out at 2,000. Ay plus By minus 4,000 times 2, 0. Ay would be 2,000. So if I have the equation right, those should be the values.
So you want negative? It should be.
There. There. Thank you. This is correct. Okay. So now I have to cut it first. Again, between any two concentrated load, I have a section. So I have to go there and cut it somewhere there. So maybe somewhere here. So section 1. So for AB, for section AB. But I have it. There. And then I have AY, which is 2000 done. And then I have N, B, and M. And remember that I choose this direction because these are the conventional positive direction. And this is going to be the section 2 here. Section 1, sorry. And the X, it will start again from, X is going from here, section, and the X would be between 0 and 4. So if I write a sigma of x0, gives me the n is 0. If I write a sigma of y0, gives me the v would be negative 2000 newton. If I write a sigma m0 about that cross section 1, then it would be but here, so I have the 2000 times the arm for the 2000 is going to be the x, and plus n. So m would be minus 2000 x. Right. So for that section, this is my V, this is the M. So very similar to the previous one up to here. Next one, I'm gonna, after the B, anytime I have a distributed load, I have to have a section in the middle of that distributed load. So again, it happens both the force change and also I have distributed load. So I have to go and cut it somewhere there. So I assume I cut it there. So for BC,
Would this be BC even though we're not traveling all the way to C?
you want to find the limit that you're using. It starts from the B and end at the C. Go there. And then I'm gonna have 2000 here, onward. Then I have BY 10,000 off. So for distributed load, the external force, what I would put there?
We want to find the center point, really put it into just one force, find single force. So we have that for 4,000 down in the middle.
So can I go there and say 4,000 there? And this is 1 meter. Remember, I told you last time, anytime that we have a distributed load, don't touch the load until you cut it. The reason for that is that if it would be correct what you say if I consider the entire things, but there's a part of that is not considered there, so it's going to be a smaller than 4,000, correct?
Yeah.
And because it's a smaller, it's not going to be there, it's going to be shifted a little bit further to the left. So what you would do, and I was asked you to do, is that don't touch the distributed load when you cut it. After you cut it, then you go there and try to replace it. So just leave it there, 4,000 Newton per meter for now. X from the very left to the section. And this distance is 2. Meter. How much is this distance?
Should be X. Yeah, I feel like that part 4.
Or is it 4 or is
Is X minus 4? Yeah, that's what was tricky.
So this distance is going to be x minus 4. And then I have my normal, shear, and moment. And now I want to calculate this. So sigma of x is 0. N would be 0. Sigma Fy would be 0. Now I have to have the value for that. So how much would the value for that force now?
4,000 times X minus 4.
Yeah. So it's going to be 4,000 times x minus 4. That's the value of that. So when I write it there, so I have negative 2,000 here. Then I have plus 10,000 there. Then I have negative 4,000 times x minus 4. Then I have minus v would be 0. If I have it right, v comes out as minus 4,000 x plus 2,400 Newton. Next, I have to find a moment. Again, I have to write a moment about that section. This is a section 2 here. Here, what I cut it is section 2. So I will write a moment about that section 2. 0. Clockwise positive. So if I write it from there, so I have the 2,000, it's going positive, so it's going to be 2,000 times x. Correct? 2,000 times x positive. 10,000 times what's the arm for the 10,000?
X minus 4.
X minus 4. And it's going to be negative because I go clockwise. What left? This guy. So the next one is that 4,000, x minus 2. And what's the distance?
X minus 4.
X minus 4. How much is that distance?
Also, X minus 4.
This distance?
X minus 4 minus 2.
X minus 4 divided by 2.
Yeah,
So
that would make sense.
that distance is x minus 4 divided by, this is half of that x minus 4. It's going to be x minus 4 divided by 2 should be 0. It's going to be this plus or minus plus. Again, if I have it correctly, m should comes out as negative 2,000 x squared plus 24,000 x minus 72,000. So now in that length, this is the V and this is the N.
Is the V always the derivative of
Yes.
So the derivative of what? Oh.
So the point that in this problem I really want you to remember is that if there's a distributed load, don't touch the load, bring it here, and then after you cut it, then replace it with the equivalent force. Okay. Now that I have this, I have to go ahead and draw them. So go there, start drawing them. I have is V is M. Then I will bring down these points. Down this one. And then I can go ahead and start drawing them. So for the V, it's simpler. It's negative 2,000. I'll do it here. And then it is from here to here, change to that. So look at here. When the x is 4 here, it's negative 2,000. When x is 4 here, how much is it going to be? So it's 16,000 minus plus 24 plus 8,000. So you'll see that it will jump up from minus to 8,000. And if I put x equal to 6, remember that here, I didn't write that here, x would be between 4 and 6. So that's the 4. If I put 6 there, it becomes 0. So it goes back down to 0. So if you jump up there, it goes back to 0. So for the moment, if I put the x 0, would be 0 in this equation. So if I put it 0, it's going to be 0. If I put the x 4, it's going to be minus 8,000. And going down linearly. And here, so you can take, if I put 4 in that equation, put 4 in that equation,
Negative 8,000.
get again negative 8,000. And then if I put 6, what's that?
0. I typed my name wrong, but yeah, it's 0.
So if you put it there, it will go 0. Is it going linearly?
No.
No, because it has a power of 2. So you can find a couple of points in between them or use your calculator to draw it for you. Eventually it goes something like this. So if I want to design that beam, again, the worst case scenario for both shear and the moment is going to be at the same point, and it's 8,000 here Newton and 8,000 Newton meter for the moment. So I have to design it for that section. Any question up to here? I'm going to give you a couple of points about these diagrams that helps us to draw them more easily. As I said, we will use them in the strengths of material a lot. So. a couple of points about this one. As we said, the D level so if I take a derivative of that, it will give me this. So here, what was the equation here?
Negative 4,000x plus 24,000.
Negative 4,000x, and if I make a derivative of that, it gives me the 4,000. So what is this one? dv over dx. Is the slope of the shear, correct? This is slope of shear. So the slope of the shear is equal to what? Distributed load. The next one is that go there. dm over dx would be so dm over dx would be so again dm over dx is the slope of the moment. So slope of the moment is equal to shear. A couple of points. Concentrated load causes the shear jump in the direction of the load. So look at here. How much was that AY? Was negative 2,000, correct? How much was this one? 10,000, correct? But look at here. Negative 2,000. It pushed down the negative 2,000. You go there, concentrated load, 10,000. It pushes up 10,000. So the concentrated load push the shear up or down equal to amount of that load that we have, or that force that we have. So sometimes when you draw it, you can just say, okay, this is 2,000 down, so it should go down. Go there, so it's the 10,000 up, so it should jump 10,000 up from that point. Any point that the shear is 0, if B is 0, M would be max or mean. So, look at here. It goes through the 0, because the moment becomes max. Or other way around. If the M is max, for mean, the shear should be 0 there. So anytime that you're going to have the maximum N, you have to look for the 0 moment in your graph. And the next one, if your N support and emphasis on that, or N support is pin or roller, then moment is 0 at that support. So, if N support, look at here, that's the pin and that's the end. So the moment will be always 0 there. This is the roller, but it's not the end support. It's sitting somewhere in the middle of that, so the moment is not 0 there. If it was here, then it will be also 0. So if you have a pin or roller at the end of the beam, the moment is always 0 there. Question?